Hello world, my name is Moses Mushabe and today we are presenting our idea and our group is SWML group 12. Uh, these are the keywords we are going to focus on, and basically we are going to talk about adaptive scheduling, artificial intelligence, Bayesian approach, cities and towns, and the rest of all of that. So let me take you through what we have. We are going to start off with introduction, but let me start with background. Let me start off with background and an introduction. Our problem basically is we are solving traditional academic scheduling. So if you look at the timetables of today, they are fixed, and it's usually a mind that sits down and thinks about the timetable and the timings of students' lectures and stuff like that, and so they sit down and schedule spaces for them to study. No, now it's static like that, and so it's unpredictable because there are a bit of changing factors in the environment. That's what we are calling unpredictable local stressors, like weather, traffic, and other bottlenecks that may come up. So this timetable remains static even when other external factors change. It just remains static. Inconveniences come in, but it remains static. You have to be there for the lecture even when it's raining. So it's a bit of an inconvenience, and so we come up with this sunk cost effect at Makerere. For example, we are taking Makerere as our study area focus. So sunk cost is about the students spending their time and all these unrecoverable resources like money only to find the lectures cancelled or unfeasible. For example, you come to class and it has been cancelled because communications are passed on later on. But if you had such a system like this we are proposing, it's a bit easy. Then causes, we look at lecturers getting stuck in traffic, sudden downpours, we're talking about rainfall, unannounced meetings. Let's go on to the next slide. Related works with this. So study has shown, and literature on the web, that current status of today, we have algorithms like I've talked about that predict the schedules of programs. So they sit down and draft a timetable for us to follow. And then recent trends that are coming up, we have the predict and prescribe frameworks. Same thing, sit down, predict, prescribe. Then reinforcement learning, it's also ongoing. Multi-agent and federated learning systems also on the move. So gaps in between the literature that we studied and what we are proposing is the existing models focus on internal factors. So they focus on rooms, faculty, courses, things like those, and then they don't focus on external stuff like rainfall, traffic. So even when traffic catches you, you have to make it. You don't get to give excuses about that. You have to make it at campus. And limited attention to external urban stressors. That's what I've just explained. It intertwines with the other one. Student commute barriers like time and cost. That is the sunken effect. And robustness and causal reasoning remain unexplored, not at all. So when I talk about causal reasoning, it's all about things that affects the schedule that are not even explored at all. Yeah. So let me take you through the next, and I'll call my colleague. Then we have the next slide that talks about problem statements, and I'll just focus on the computation side of it. So we need a lot of data and so many variables: weather data, traffic data, university schedules and events. A lot of data, and it requires a lot of resources to program such a model. And then too much data, like I've said, variables, and then we must solve a problem of regression, because you have to predict late sessions. uh, you have to predict how the sessions will start, and then decide on whether to hold or to delay or to go virtual. That's like predict and control kind of model. So let me call on my colleague and they will take us through the next.
So I'm continuing from where my group at Moshavi stopped. My name is Togumeki, and yeah, we had the research questions. Given given the problem statement, we came up with the following research questions. Okay, it's moving so fast. Yeah, so research questions. One, we found we had to ask ourselves, what are the key urban stressors that cause schedule failure and student commute losses at the university? The second question was, how can multi-source data be integrated together to predict schedule viability in real time? About how to integrate traffic data, weather data, and data for the administrative events. The third question was, how can a machine learning system distinguish between statistical correlation and true causal environment logic in scheduling decisions? So our objectives would be to identify the key urban stressors from the data set of weather data and the events. We'd have to identify the key urban stressors that cause schedule failures and student commute losses at the university, at Makerere University. This is our case study. So to develop, the other objective is to develop the DSTSE, the Dynamic Spatial Temporal Synchronization Engine, which integrates PCA, random forests, SVM, support vector machine, and Bayesian networks for predictive scheduling. So the objective is to simply find an intelligent predictive scheduling system. The third objective is to implement a causal audit mechanism that distinguishes between statistical correlation and the true environment logical in scheduling predictions, to also evaluate the framework's effectiveness in reducing the frustration index. Frustration means anger, so we are trying to measure the anger. Frustration index compared to the traditional static timetabling methods, whereby the timetable is written in stone, come rain or shine. And so this was the DSTSE. Let me see, is it visible here? I'll zoom in a bit on the second screen. Yeah, the DSTSE architecture. We used an 8-layer taxonomy. So the layer 0 was to have the objective, which we've stated back there. We have 3 data sets being combined into integrated. So then we have a temporal synchronization, which is our 3rd layer, the data structure, and the perception layer here, where we are using the first model, which is the PCA, and dimension reduction, so that we can have 3 pieces. And then we go to the next layer, layer 2, let me see, which is the predictive path and the causal path, where we're combining random forests and Bayesian network separately for the respective predictive path, Bayesian forest is symbol, and then causal path for the Bayesian networks. Then we move to the layer 1, which is consensus and audit, the audit loop. Then policy enforcement, whereby we use the SVM, hard and soft margin to prevent event type. Yeah. So we also had the, let me see, yes, we had the, let me zoom in again, schedule action, and so that's the layer 6. Then lastly, we'll go back to a feedback loop that pushes back to the Bayesian networks. So that's our iteration is, yeah. So we have a data description, and I'll use this. Yeah, so we had the total number of columns is 50 for temperature, which is the highest. We also had the mean as for each for each weather statistic, and then light rain was 95% and the extreme rain was 16 occasions. Yeah, and we also had event types for the traffic, political unrest being 48, diplomatic, VIP movement where the sirens, we have a bullion van, for example, an ambulance, we have a bullion van pushing vehicles aside, which would cause traffic congestion. Also, when there's a political move like a campaign or something, a natural disaster, a floods in let's say Boise, if some students come from that side, or accidents, and maybe a security operation. Yeah, basically that was the integrated data, and that this was the architecture that was used. So I shall call upon my group mate to proceed from here. Thank you.
All right, hello everybody. So my name is Timba Fahad. So I'm here to take you in this next chapter that follows the previous speaker or presenter. So these are some of the visualizations of the data that we managed to collect and bind together. We had a bunch of data sets, so we had to put them together. However, before we put them together, we had to analyze data set by data set. So not to go further, let's start right away in here. So let me start with a heat map. Let's start with the traffic data that we try to analyze, and let's divert to the heat maps. So these heat maps, we can see that yes, the dark regions, they indicate the high traffic, just like you could see on the scale on our right. Let me try to zoom in, and you see here, yes. So we can see we had 4 routes that come to Makere, lead students and lecturers to Makere University. We have the Sir Apollo Road, we have the Bombo Road, we have the Northern Bypass Road, Wandegea Road as well, even the Kampala Road. So we tried to combine these two and visualize them, but we saw that these have some related correlation, and we can see that the dark region is always on Friday, and we hope, I think this is when people go for weekends, go to have good days with their lovely families. So we hope, that's why I think we see this dark region, or many cars or high traffic. Yes. So also on we can also see on the global complexity of this combined data, or having anomaly regions, and we can see it in 2013 January, and also it was a public that was a culture festival. Those are referred to as culture festivals, just like my previous presenter who has talked about some various events that cause traffic, the causal problem, the causal effects for this traffic. And we talk about the public holiday, just like you can see the second one, and it happened in 2023. Then we also talk about the green one, which is the exam week. Yes, exam week. And also the strike protests, and it spanned for a small time. Yep. So that is some simple. But the next about traffic again is so let's try to make drive some correlation and some pie charts for this these different routes. So with the correlations, we can see that it's how are these routes correlated. This was before putting them together or imputing. Get the point? So route 1, it correlates, it has, these are the correlations with other routes, route 3, route 4, route 3, and route 2. And the same applies route 2 with other routes, route 3, route 4, route 3, and route 1. We can see that they are a little bit close to one another. Yes. So also for the pie charts of the business of these routes, we can try to derive some insights in here. That normal takes the biggest percentage, and as well as heavy, high, and low takes the low, meaning the less chances of route 1 to be to have low traffic. There are less chances compared to when it's normal. or compared to when it's high or compared to when it's heavy. The same applies root 2, root 3, root 3 and root 4. All right, jolly conversation. So we talk about this correlation heat map, correlation matrix for the combined for our combined data, and we try to see that. All right, so to continue up with our jolly conversation, we go to the line graphs to showcase the traffic progression through all the years. So, all right, perfect. So here, to not to take a lot of time, we can see that we try to visualize this hourly for these routes, but we can see that in the morning hours the traffic is really low and it escalates or increases slowly as time goes by. So we can see that it reaches its peak in the morning hours. This is when I think when people are going for work, and it decreases in the afternoon hours. So it also now goes a bit high again, or it picks up in the late hours or in the evening hours. I think that this is when people are getting off work. So yes, and also we try to also go to weather, not to take out of time on traffic. We can see this is its visualization, that its time, it's we can try to, let me try to zoom in here. Yes, the traffic over time for all the years. So we can see these patterns are repeating themselves on these routes. All right, so moving on to the next slide of weather, we can see that weather here, we can see that as temperature increases, let me try to zoom in. Yes, as temperature increases, humidity goes low. We can see that there's a negative correlation between these two, or negative gradient. So as temperature increases, humidity also as temperature increases, humidity decreases. So here means that more temperature. This could mean that as temperature increases, less humidity, low rainfall, and also now this could be less traffic in other way around. So we shall try to find out the relation between this and back, and also we can try to find out here that when temperature increases, this we try to record the weather hourly graphs of weather or of temperature against the day. So you can see that in the morning hours temperature is always low, and it goes high when the day like sun rises, noontime, then temperature reduces in the evening. And we also try to see that they relate, but negatively. It's inverse. So as time goes by, or as hours increase, humidity also in the morning hours, we can see that humidity goes high, and it reduces when the sun goes high or when the temperature goes high, just like this. Then humidity then goes high in the evening hours. Yes, so